4 recordings can look extraordinary for 4 completely different reasons. A real object can be distant. A slow object can appear fast. An infrared source can look larger than it is. And a tracker can move even when the target does not accelerate. So before asking, what is it? We need a more basic question. What does this video actually measure? We will use one rule throughout. First, what is directly seen. Second, what the instrument measures. Third, what geometry allows us to derive. And finally, what the public data do not determine. An infrared camera does not record ordinary color. It converts infrared radiation reaching the detector into brightness. The display may show hotter regions as white or reverse the polarity and show them as black. The physical scene has not reversed, only the mapping has changed. Now consider one bright patch in the image. Its width gives an angle, theta. It does not immediately give a physical diameter. A small nearby object and a large distant object can occupy exactly the same angle. For a small angle, physical diameter is approximately range times angular diameter. D is approximately r theta. Without the range r, D is not unique. The same problem appears in motion. The image gives an angular rate, omega. Transverse speed is range times angular rate. V perpendicular equals r omega. The same screen motion can represent a slow nearby target or a fast distant target. And if the camera is moving, its own velocity must also be included. FLIR 1 was recorded by a United States Navy aircraft in 2004 and officially released by the Department of Defense in 2020. The tracker keeps an infrared contrast near the center by steering the sensor's line of sight. During the recording, display mode, polarity, and magnification change. Those changes affect the image without requiring the target itself to change. The public clip supports a direct statement. The sensor tracked an infrared contrast, but physical size needs range. A complete three-dimensional trajectory needs range, sensor attitude, aircraft motion, and calibrated time samples together. When a tracker loses lock or the contrast leaves the frame, the image alone does not measure a sudden acceleration. The sensor may have failed to follow an otherwise continuous path. FLIR 1 is officially unresolved. Here, unresolved means that the released information does not determine a unique identification.
That's not our LNS though, is it? It's not.
That is the LNS, dude.
Well, if there's like...
Look at that thing!
It's rotating.
The Gimbal recording, made in 2015, contains a striking visual event. The infrared image appears to rotate, but the angle in the image combines 2 different angles. The displayed orientation equals the physical orientation of the source minus the orientation introduced by the sensor and its optical path. If the object turns while the optics remain fixed, the image turns. But if the optical frame turns while the object remains fixed, the image can also turn. An unresolved infrared source may be broadened by glare and by the point spread function of the camera, so the visible shape need not be the physical silhouette. This does not prove an optical explanation. It identifies an ambiguity. The supported observation is that the infrared image rotates. The public clip alone does not isolate how much of that rotation belongs to the object and how much belongs to the imaging system.
Nickel 6-1 Tango Roger, over.
Oh, got it! Woohoo!
Roger, there's troubleshooting.
Did you box moving target? No, I took an auto track.
Oh, okay.
Oh.
GoFast was recorded in 2015 by a Navy F-18F over the Atlantic. Unlike many short clips, its display contains several quantities that constrain the geometry: aircraft altitude, slant range, sensor azimuth, sensor elevation, airspeed, and time. Begin with altitude. Let h be the aircraft altitude, r the slant range, and alpha the downward viewing angle. In a flat Earth approximation over this short distance, the target altitude is h minus r times the sine of the absolute viewing angle. Using representative display values, about 25,000 feet for h, about 4.4 nautical miles for r, and about 26 degrees downward, the vertical drop is roughly 11,700 feet. That places the target near 13,000 feet, not just above the ocean surface. Now look at the rapid ocean motion in the background. The camera is carried by a fast aircraft. As the aircraft translates, the line of sight pivots across the nearer target and the much more distant surface. This is motion parallax. The angular rate is measured from the changing line of sight, but the relative transverse velocity is r omega, and it contains both target motion and aircraft motion. Assigning all screen motion to the target gives the wrong physical story. RO evaluated the possible aircraft headings because the exact heading and location were unavailable. Across those solutions, it estimated the object's speed relative to the wind from approximately 5 to 92 miles per hour. The apparent extreme speed is explained by motion parallax, and the analysis found no anomalous performance in the public recording.
We got a lot of white water out there, some 6-foot swells.
Whoa, it's getting close.
Yeah, we have 31 knots sustained wind, topside, gust of 40.
Whoa, splashed. Mark bearing and range.
In the USS Omaha recording, a dark tracked image descends toward the apparent sea line. Near the end, an operator says, "splash," as the image disappears. The spoken observation matters, but it is not the same as a measured intersection with the water. A camera compresses 3 dimensions into 2. Different paths in space can approach the same line in the image and then become hidden by the horizon, contrast loss, or tracking loss. To establish water entry, we would need range as a function of time, the camera pose, and a trajectory intersecting the measured sea surface. A second viewpoint would provide triangulation. Synchronized radar could test whether the track continued. A resolved surface disturbance would add independent evidence. The public clip supports this statement. The tracked image disappears near the apparent sea line. From that clip alone, entry beneath the surface is not determined. Recent official releases add more imagery, but not every release adds the measurements needed for identification. This infrared image was described by its appearance as a 6-pointed star. That phrase describes a detector image, not necessarily a 6-pointed physical body. When a source is smaller than the camera can resolve, optics spread one point over several pixels. Aperture geometry, focus, saturation, digital sharpening, and compression can create lobes or sharp-looking edges. The correct question is whether the pattern rotates with the object, with the sensor, or with the image processing chain. An unresolved case can simply mean that available data are insufficient for a definitive attribution. It does not, by itself, establish unusual speed, propulsion, or material properties. Now we can ask the harder question. Could one of these observations represent an unrecognized technology or even new physics? The answer begins with an evidence ladder. At the first level, we have pixels and a witness report. They can reveal that an event deserves attention, but they rarely determine distance or speed. Next come calibrated optics and precise timestamps, then range and the full state of the observing platform. Then synchronized independent sensors such as radar, infrared, visible light, and a second viewpoint. Only after those measurements agree can we derive velocity and acceleration with uncertainty bounds. A repeatable spectral, thermal, inertial, or electromagnetic signature would raise the evidence further. Unrecognized technology becomes a serious hypothesis if robust kinematics survive checks for geometry, atmosphere, sensor response, and known vehicles. New physics has a much higher threshold. It requires repeatable quantitative measurements that contradict tested models after systematic errors and known technology have been excluded. A low-resolution point moving across a display cannot, by itself, reach that threshold.
My testimony is based on information I've been given by individuals with a long-standing track record of legitimacy and service to this country.
Testimony has a different scientific role. It can identify witnesses, records, sensor files, and gaps in oversight. It can tell investigators where evidence may exist. But testimony is not a calibration file. A reported conclusion cannot replace the range, timestamps, sensor model, and platform state needed to calculate a trajectory. The useful next step is therefore concrete. Preserve original files, establish chain of custody, release calibrated data where security permits, and let independent teams reproduce the analysis. What then are these sightings? GoFast has a constrained result. Its dramatic apparent speed is consistent with motion parallax, and the available display data do not show anomalous performance. FLIR 1 and Gimbal are authentic official recordings, but their public form does not uniquely determine the objects. The USS Omaha clip shows a disappearance near the sea line, but does not by itself measure underwater entry. Recent infrared clips may remain unresolved because the public data are too sparse. The possible explanations include distant aircraft, balloons, birds, drones, atmospheric contrast, optical effects, sensor artifacts, or technology not identified from the released evidence. A scientific analysis does not choose among them by excitement. It asks which new measurement would force the alternatives apart. Unknown is not a kind of object. It is the distance between a question and the measurement that would decide it.